Welcome, dear students, to Pen and Paper Chemistry on YouTube.
Continuing with our topic D and F block elements. Now in this particular topic we shall be talking about the properties of elements of D and F block, but more specifically actually the D block, and we shall be talking about the periodic properties. Now in order to aid me in teaching, I have got a chart over here wherein I have listed the metals of the 3D transition series. Horizontally I have put the electronic configuration. So if you notice over here in this chart, again I am using an old calendar. So I've got listed over here the atomic radii, then I've got the ionic radii. Of course at the top we've put the electronic configuration, followed by the atomic radii, ionic radii, then I have the ionization enthalpy, the first ionization enthalpy, then we've got the electrode potential, melting point, boiling point, density, and of course the oxidation states. Now with this chart what I have got is I have got an overview which will help us to understand the properties based on the electronic configuration, right? So one, with the help of this chart we will be able to see the variation in the properties. Second, with the help of this chart we will be able to correlate the variation with the electronic configuration. So let's get going. Now we already know that the transition elements, the D block elements, are metals. They are hard and brittle. They have high melting point and boiling point. They are good conductors of electricity. Now you must be wondering why I am listing the properties, all the properties of metals, because these are the properties which are shown by the elements of D block. So again, the characteristic properties: metallic luster, ductility, malleability. I hope you all are familiar with these terms. Ductility is ability to be drawn into thin wires. Malleability is the ability to be beaten into thin sheets, right? Now all these properties are shown by elements of the D block. Let us correlate these properties to their structure. So let's get going first to the electronic configuration, about which we have already spoken. So I am going to quickly brush through it, and then we go on to the atomic radii. So what we've got over here is we've got the elements of the 3D series listed over here: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Configuration: 4s2 3d1, 4s2 3d2, d3, d4. Is it d4? No, it is s1 d5. Again, we've already done this. Go on to atomic radii. Now let us see the variation of the atomic radii. A request over here: if you can make this chart paper yourself on some A4 size sheet, it will be much easier for you to understand this, because I am not able to take a close-up of this chart every time I have to explain. Sorry for that. So if you see the atomic radii, 144, 132, 122, 117, what is happening to the atomic radii? Yes, it is decreasing. So let us first study the atomic radii of these elements. So our first property that we are doing is atomic radius and On moving along in any series, the atomic radii, and specifically we are studying the 3D series, the atomic radii decreases, right? But if you go on, you see there is stability over here. Chromium, manganese, iron. Atomic radii is same, 117 picometer. Cobalt, nickel, copper, zinc. Cobalt, nickel, copper. There is slight decrease again. And coming to copper and zinc. Copper again 117, zinc 125. So if you see an element with atomic number 29 is having atomic radius 117, whereas zinc all of a sudden shows an atomic size of 125. So we need to study this behavior of the atomic radius. What do you think is the reason? One major trick that I am going to tell you in this particular chapter. The entire trick in this chapter is the electronic configuration. Most of your, I am not saying all, most of the explanations or reasonings in this particular topic can be done on the basis of electronic configuration, right? So, let's see the electronic configuration. Oh yes, you already know it. Because we are filling up the electron in the penultimate shell. So, we have the configuration 3D1, 4s2, 3D2, 4s2, 3D3, 4s3, right? When moving along the 3D series, 4s2, 3D4, no, it's 3D5. And where do we land? Scandia, Ti, VCr, right? Go on to manganese again. So it will be 3D5, 4s2. If you see the electronic configuration, whenever we talk about the atomic radii, it is being governed by the nuclear charge and also by the valence shell, right? In the case of these elements, nuclear charge is increasing by one at a time. So we start with 21, 22, 23 and so on. So nuclear charge we know is increasing. What about the valence shell? The valence shell is remaining the same. The valence shell in each of these cases is the fourth one. So where is the electron entering? The electron is entering into the penultimate shell, one inner to the outermost. The nuclear charge, what is happening over here is, the nuclear charge, because of the electron entering into the penultimate shell, the force of attraction increases. But not to such a great extent, because they start encountering what we call as the shielding effect. But at the same time, the shielding effect is because of the presence of d electrons. Now, because this shielding effect due to d electrons is not so strong, what will happen is, if you notice, there is not much variation in the atomic radii, but it is decreasing as we go towards the middle of the series. Coming to the center of this. Now in the center we've got chromium, manganese. What do you see over here? 3D5, 4s1, 3D5, 4s2. What does this remind you of? Yes, it's the half-filled and the fully filled orbitals which are extra stable. Moreover, what happens over here is that each of the electron or each of the orbital is singly filled up, right? 3d5 is what it indicates. So the electronic configuration being similar, we find that there is no change in the atomic radii between these three elements, chromium, manganese and iron, which is 117, right? Now what happens after this? Again, there is not much change, it's 116. What accounts for this? Because from iron onwards, what happens is the electron starts pairing up. This is what we have. So the exchange energy is also reducing over here, because of which we find that the atomic radius does not vary much. You have to remember that because of the pull between the proton and the electron, that is because of the nuclear charge, there is attraction. But as we keep adding electrons, there is electron-electron repulsion as well. Because of this electron-electron repulsion, it will show a slight increase. And this becomes very prominent when all the electrons are paired up. And where are all the electrons paired up? 125 in the case of zinc, where the configuration is 4s2 3d10. So because it's S and P electrons are completely paired, S and D electrons are completely paired up. The interelectronic repulsions being higher, the size of the atom in the case of zinc. Similarly, when you will go down the series, zinc, cadmium, mercury, in that particular order, 3D series, 4D series, 5D series, the atomic radius will be exceptionally higher compared to the elements before it. So they actually break the rule of that particular series. So this explains atomic radius. Now once we've done atomic radius, we can easily do the ionic radius also. Why? An ion is formed by the loss of electron, right? How many electrons can be lost? Any number. So you can have 1 electron being lost, you can have 2 electrons being lost, you can have 3 electrons being lost, right? That's how an ion is formed. And at each stage, the ionization energy is different. Again, if we see the ionic radii over here, it is showing a similar trend. I will read out the values to you. It changes from 90 to 88 to 84, 80. See, there is a decrease in the value for the same reason. Nuclear charge is increasing, the valence shell remains the same, electrons are being added into the penultimate shell. There is shielding effect of the d electrons, but because of their diffuse shape, the shielding effect is not so strong, with the result the size of the atom actually decreases. Comes down to 74, 72, 72, 72, 79. Now if you notice over here, cobalt, nickel, copper, when I am talking about the formation of M2 positive, here the stability is coming, or same value is coming from CO2 positive and I2 positive, Cu2 positive. What explains this? Yes, the loss of 2 electrons takes place from S2 configuration, resulting in electrons only in the d orbital. So just take the electronic configuration and it answers most of your questions, right? Let's go on to correlating the atomic radius to the density of the elements in any particular series, the 3D, 4D, 5D. Density is nothing but mass per unit volume of a substance, and this we know from our knowledge in physics, right? What is happening to the mass of the atom as you are going across in any series? It is increasing, because we are talking about atomic number, scandium, titanium, vanadium, and so on. So what is happening is, as we are advancing, the atomic mass is also increasing. What is happening to the size of the atom? Just now we discussed that the atomic radius actually decreases, right, due to increase in the force of attraction between the nucleus and the electrons present in the outermost orbit. Because the size of the atom, now size of the atom is nothing but a measure of the volume, right? Mass is increasing, volume is decreasing. So what will be the net effect on the density? Yes. So when you are talking about across the period, the density actually increases. What will be the exception here? Yes, wherever you have the mass increasing, and that is at the end of any particular series. So zinc, cadmium, mercury, these elements, because you're talking about down that particular group, the density will be lower because their atomic mass is higher, right? Atomic mass is higher and volume is also higher because their radius is more compared to the previous element, right? So three properties we have covered now. Let's go on to the fourth one, that is hardness. Hardness is our next property. What explains the extremely hard nature of these elements? If you see the electronic configuration, now in the case of the S and the P block elements, it was your valence electrons which were participating in bond formation. So when we were forming a molecule of nitrogen, it was the electrons in the valence shell which were participating in forming the triple bond between the two nitrogen atoms. This is where the transition elements go a step ahead, because in their case you do have the electrons in the valence shell. They may be either complete or incomplete, but at the same time they have unpaired electrons in the d orbitals of the penultimate shell. And not just the s electrons of the valence shell, the n minus d electrons also participate in bond formation. Now what type of bond formation? There are different views to this. It is metallic bonding, but according to new theories, it's a type of covalent bonding which is explained in terms of overlap of the unfilled d orbitals of the penultimate shell, right? So what we've got over here is, we've got the hardness explained on the basis of the number of unpaired electrons in any atom. So more the number of unpaired electrons, more is the tendency for them to go and find some partners so they can overlap, so that they can complete these electrons. So let's suppose if I am talking about scandium, right? Ns2 and n minus 1, 1, 2, 3, 4, n minus 1 d, right? So here we've got 4s2, 3d1, there is one unpaired electron. Go on to the next one, two unpaired electrons, titanium, vanadium, s2d3. Go on to the next one, chromium, s1d5. Right? Maximum number of unpaired electrons. Very hard. In fact, I think it's the fourth hardest substance, right? So, because the number of unpaired electrons is very high over here, right? Same way, if you see the elements under chromium, molybdenum, tungsten in this particular group, so we are talking about group number 3, 4, 5, 6, we are talking about group number 6. This constitutes of some of the hardest metals, some of the hardest transition elements. Coming to manganese, now what happens is it starts pairing up S2D5, iron S2D6, cobalt S2D7, nickel S2D8, copper S2D9. Is that correct? No. What happens over here? Yes, the electron jumps from here and we have a fully filled d orbital, right? Because of which, yes, it is not such a hard metal. Come to next, zinc. All electrons are paired up, so the possibility of overlap becomes even much less. That is why if you see group number 12, zinc, cadmium, mercury, you have the soft metals. In fact, mercury is existing as a liquid, right? So you have to again explain hardness on the basis of the electronic configuration and the type of overlap which is taking place because of unpaired electrons in the ns and n-1 d orbitals, right? Let's go on to the next property then. Let us now correlate our understanding to melting point and boiling point. Melting point means you heat the substance, there is repulsion between the particles, they start moving faster and the substance turns into a liquid, right? You heat this substance further, the particles acquire energy, the particles will move further away and it turns to a gas. Oh teacher, this is simple knowledge, we have been learning about it since class 6, so what is so new about it? Nothing. You just apply it to the learning that you have till now of the D block elements. What you've learned is that with increase in the number of unpaired electrons, the forces of attraction are increasing. The extent of overlap is increasing if you are considering it as a covalent bond in terms of the bond theory. Because the extent of overlap is increasing, the force of attraction between the nucleus and the electrons is also increasing, right? They are holding the electrons of each other strongly. Or if you consider it as a metallic bond, then also because of the smaller size, the force of attraction between the nucleus and these electrons is increasing. Now, if they are having forces of attraction for the same common thing, they will come closer to each other. Closer means, will you have to give low energy or high energy to separate them? Definitely high energy to separate them. So, what do we notice about the boiling point and melting point? Let me read out the values to you. I am going across the period. So, 1812. 1998, melting point has increased further because the number of unpaired electrons has increased. 1, 2, 3, 4 and 5. So we've got S2, D1. Then we've got S2, D2, S2, D3, D4. Sorry, now it will be D5. The number of unpaired electrons is maximum. And then starts showing a decrease again. Since the number of unpaired electrons is decreasing, we notice that the melting point also starts showing a decrease. So when for scandium we had started at 1812, for cobalt it is 1769, followed by nickel 1726, followed by copper 1356, and zinc 693, quite low. As I said earlier, mercury is a liquid, so the trend goes down in a group as well, right? Here's an anomalous behavior which is shown by manganese. See, it should be increasing. So manganese actually has 5 unpaired electrons. It's S2D5. It should have even higher melting point, but we notice that the melting point of this is actually lower than chromium. I have been trying to understand why it is so, and the only plausible explanation that I have come across, although it's not quite convincing, is the extra stability of the half-filled orbitals, because of which this is not so strongly attracted by the nucleus of the second atom, causing the extent of overlap to be lower than what we may expect theoretically, right? Similar behavior is also shown by TC, technetium, when you are going down in this particular group. So we'll have group number 3, 4, 5, 6, 7. Down the 7th group, again we notice technetium, the melting point is much lower than expected, probably because of the same reason, right? Come to boiling point. Again, 3003, 2536, 3723. Again, there is a variation and there is an increase in the boiling point. Yes, there are anomalies, 1 or 2 at certain places, but those can be explained on the basis of their electronic configuration, the difference in their electronic distribution. This is where the transition metals or transition elements are slightly different from the S and the P block. So out of the properties that I have listed on this chart, we've taken care of atomic radii, ionic radii, we've spoken about melting point, boiling point, density. We are left with few more properties other than those listed on this chart. Have you noted this down? We go on to the next property. Ionization enthalpy, energy which you require in order to remove an electron from a neutral gaseous atom. Now this is its exact definition. Ionization enthalpy, now we are going to take a generic view. That means simply the amount of energy you need in order to pull out an electron from a neutral gaseous atom, from a neutral atom. Simply, I've got an atom, I want to remove an electron from it, how much energy will be required? Simple logic. More the stability of the configuration, more is the energy which is required, right? On the other hand, if you are removing an electron and it is making it stable, then definitely the ionization enthalpy or ionization energy will be lower. Some points to be noted over here. Here I have listed the ionization enthalpy in blue for the 3D transition series. If you see the first ionization enthalpy for scandium, that means when you remove one electron. Second ionization enthalpy when you remove 2 electrons. Third ionization enthalpy when you remove the third electron, and so on. If you notice the value of the first ionization enthalpy for scandium, which is 631, and compare it to immediately before it the atom calcium, which has got the atomic number 20 just before it in the periodic table, but belonging to the S block. Compare the values. This is 589, this is 631. Why is the first ionization enthalpy of an element in the D block more than the first ionization enthalpy of an element in the S block? Can you think of a reason? You may like to pause the video, write the electronic configuration and try to give the reason yourself. The reason is entirely based on what we've already discussed related to the atomic radii. There's a hint that I have thrown to you. Try giving the answer and then continue with your video to get the answer. Yes. You see, in the case of calcium, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Right? Whereas in the case of scandium, now this is we are talking about calcium. In the case of scandium, there is 4s2 and 3d1. So the electron is entering into the d sublevel of the penultimate shell. See, this is what I told you. The whole trick of d block elements is the electronic configuration. Because the electron is entering into the d block, what is happening is, yes, there is greater force of attraction between the nucleus and the outermost electrons, because these d electrons are not able to give that much shielding effect. So they are holding, the nucleus is holding the electron strongly. So you need to give more energy in order to withdraw the electron, right? On the other hand, when you come to the second ionization energy, here, if you notice, there's a sharp increase. 631, 1, 2, 3, 5 is the second ionization enthalpy of scandium. Again, can you reason on the basis of its electronic configuration? See over here, when it is Sc positive, its electronic configuration is 4s2 3d, 0, right? Now if we need to move the electron, this will be 3d1 and the electron will go off from 4s1. Now what is there is Sc positive. Here we need to remove the electron from the 4s1 orbital, but there is a positive charge on scandium, right, which is going to pull the electrons in the valence shell even more strongly. And you have to remember that this is still stable because it is half filled. Earlier it was fully filled and now it is half filled. Correct? Go on to the ionization enthalpies for the other elements in this period. You notice 631, 656, 650, 652, slightly increasing. Although there are few anomalies, we can explain it on the basis of the electronic configuration. Come to manganese, 717. See, something interesting. Its atomic radii was 117 and ionization enthalpy, first ionization enthalpy is 717. Can you give me the reason why it is so? 717. Perfect. Stability of half-filled orbitals, because the half-filled orbitals are extra stable. Manganese configuration is S2D5. S2 is fully filled, D5 is half-filled, because of which removal of the electron becomes difficult. Something interesting over here, you see zinc is 906. So is it easy to ionize zinc? No. It's exceptionally high. Reason? Yes, because of the stability of fully filled orbitals. We've got the configuration of zinc as S2D10. Now supposing I ask you to, let's say copper. Can you predict anything about the second ionization energy of copper compared to the first? Will it be high, low? Will it be easy? Which one is easier? Is it easier to remove 1 electrons or 2 electrons from copper? Remember electronic configuration. When you've got Cu, the configuration is S1D10, right? So in order to, if you are talking about removal of 1 electron, the ionization enthalpy, it will be easy to remove because I've got the configuration S1. But after we have removed one electron, now the configuration is D10. There is nothing in S. So will it be easy for us to remove the electron? What about the second ionization enthalpy? Will it be high or will it be low? Think about it. So you notice over here, ionization enthalpy 1 is 745 while the second ionization enthalpy is 1958. So you can, with the help of electronic configuration, explain why the second and the third ionization enthalpies for the elements in the transition series or the D block is usually exceptionally higher compared to the first ionization energy, right? This takes us to something, what about, okay, this takes us to, I think, the next property that we are going to discuss, and that is we are left with electrode potential, right? So let's go on to electrode potential. Ready for the next property? Let me quiz you. These questions are based on ionization enthalpy. The first ionization enthalpy, if you observe, for vanadium first ionization enthalpy is 650, whereas for chromium it is 652. So there's not much of a difference, there's not much increase when we are talking about IE1 when moving from vanadium to chromium. What is the reason? Chromium and copper, Cc, remember something different about them in their electronic configuration? The second ionization energy is exceptionally higher. The values are not listed here. Please refer to any of your textbooks to get me the values of IE2 for chromium and copper. For that reason, you will also open your textbook, right? For zinc, now usually the second ionization energy should be higher, right? Like we have seen in the case of chromium and copper. But in the case of zinc, we see that the second ionization energy is low, but the third ionization energy is very high. What is the reason? Manganese again. Third ionization energy is exceptionally high. That means in order to remove the third electron from manganese, you need a lot of energy. I'm going to throw a big hint to you over here. To answer all these questions, just write the electronic configuration. So if I'm talking about IE2, make sure that you write the electronic configuration of M plus and not M alone, because IE2 means we are talking about removing the second electron from the atom, right? So be careful of what we are talking about over here. Write the electronic configuration and you will have the answer to all of these questions. Stay tuned because we still continue with the properties of the D and F block elements in lesson number 3.